We know that everything in the universe vibrates, and molecular vibration occurs in the infrared or IR region of the electromagnetic spectrum. So we can use an infrared spectrometer to measure the vibrations that occur in a particular molecule. The responses are measured in a unit called reciprocal centimeters, which we commonly know as wave numbers. And each different type of bond, as you can see from the chart on the right, corresponds to or has its own characteristic range of wave numbers where it will vibrate. Okay, IR spectroscopy is used to identify functional groups in an organic molecule. This is what a typical IR spectrum looks like. Looks kind of like a mess. All right, this is an acetone, okay, shown here. So now the different parts of an IR spectrum from about 0 to 1200 wave numbers. All right, there were 0 to 1200 reciprocal centimeters. This is known as the fingerprint region of an IR spectrum. Now, the fingerprint region is determined by the molecule as a whole and how polarity shifts electron density throughout the entire molecule, that type of thing, how will affect the overall molecule's vibration. Now, why this is important is that just like no two individuals have the same fingerprints, no two molecules have the same fingerprint region in an IR spectrum. So if we're looking to identify a particular molecule, and we know we have, let's say, a literature value for its fingerprint region, we can compare an experimental IR spectrum to that. I'll say more on using IR to identify an entire molecule in a moment. Okay, but just know that this area of 0 to 1200, we won't actually focus on all that much as part of our course. This would be for further study in chemistry in your future. All right, let's look at the main part of the IR spectrum. All right, there's actually two main peaks that I'm going to examine in this one. So the first one you can see here occurs somewhere around 3000 wave numbers. I'm going to come over to my chart and I'm going to say, what could that be? This peak at 3000 is quite strong. Strong meaning it comes down towards the bottom of the spectrum. All right, this is a carbon-hydrogen bond in an alkane or an alkene or an arene. All right, the next major peak that we're going to look at, and probably the most useful in much of our study of organic chemistry, is this one that occurs around 1750 wave numbers. This corresponds to a carbon-oxygen double bond. All right, it's quite strong. All right, it's usually very easy to identify, and this corresponds to the carbonyl group. Okay, next up, we're going to look at acetic acid's IR spectrum, also known as ethanoic acid. All right, so here's the molecule. Let's examine the IR spectrum, and we'll compare this to the literature values from the chart. Okay, remember, you always have access to your data booklet when you're analyzing spectra, so you do not have to memorize this table 26 in any way. You'll always have it available to you. So acetic acid has this blob thing occurring around 3000 wave numbers. This blob is actually the oxygen-hydrogen stretch, so we would call it an OH stretch. It's quite broad. It always occurs around 3000. All right, it shows up as this blob. All right, and so this would be present in carboxylic acids and alcohols. Okay. The next structural feature that we'll look at is the one that comes around 1700. Okay, this is the carbon-oxygen double bond, which is also present. Okay, highlighted in purple. All right, one of the next things that we could examine here, and we might be getting a little picky on this one, that we often wouldn't ask you to identify this on a tester exam, would be the carbon-oxygen single bond that would occur in alcohols, esters, ethers. All right, you might see it in a carboxylic acid. So again, we hardly would you shouldn't actually need that for a carboxylic acid. All right, one thing I'm also going to note here is that the CH bond that we saw in the earlier example with acetone, it's obscured by the OH blob. All right, so this carbon-hydrogen stretch is often quite strong, but it's very narrow. And as soon as a hydroxyl is present in the molecule in any way, we can no longer see the CH stretch. Okay. I would like to note that IR is used to identify functional groups only for our purposes. Okay, you will not be asked to identify an entire molecule by its IR spectrum. All right, it must be used in conjunction with mass spectrometry or NMR in order to identify an entire molecule.